Right. Welcome, everyone. Today's presentation about C11 atomics by Robin. Robin interned with us in the Chrome Pinnacle team. He's a PhD student at ENS Paris, and so his internship is finishing this week. He'll be giving a same or similar talk at the LLVM Developer Conference later this week. So please keep the questions towards the end. And with that, Robin.
Thank you. So I will start by quickly explaining what these atomics are and what they are useful for, and then focus on how we can optimize them in the LLVM compiler. So the problem is how can you write a portable log-free code? Because for example, with this code, it may seem clear that you will never print 0, 0. Because if you look at all the possible interleavings of the two of the four actions, you will see that you can never have both prints come before their respective store. But in practice, you can see 0, 0 if you actually execute that code, because the most processors, including the x86 family, can reorder these instructions. More precisely, they can send the store in a store buffer and then execute the load before the store has been propagated to the other core or to anyone else. So you need some extra instruction called a fence to tell the processor, don't do that, flush your buffer and do things in order. So now, what about this code? It may seem like it will never print 0. If it prints anything, it should print 42. Indeed, on x86, you won't have any issue with this because the only tricky thing is the store buffer, and the store buffer is first in, first out. So by the time the store of 1 into ready is sent to the other core, the store of 42 into X was already sent, so no issue. But on ARM, for example, the stores in the store buffer can be sent in a different order. So you can see ready equal 1 before you see X equal 42. So on ARM, you need at least one fence here. And in practice, it is even worse, because ARM processors can also speculate the read of X and say, well, I will first read X, then I will read ready and do the branch and print whatever value I read before I saw ready. So you need another fence on the second thread to prevent that kind of things. So all this is fairly tricky, and even worse, it cannot be catched by tests. For example, if you are testing on x86, and then someday later someone will run your code on ARM, you may have bugs waiting for you. So in C11 and C11, they added ways of portably specifying where you want the compiler to introduce such fences. So in a nutshell, what the C11 standard says is that if you have a race, meaning if in any execution of your program you have two accesses to the same location with no synchronization in between and at least one of them a store, your entire program is completely undefined. The compiler can do whatever it wants. If you have locks used everywhere to enforce a synchronization, then you just have the old intuitive behavior, and you only have to look at interleaving of your actions, no tricky parts. Finally, because it is a C, you may want to write some log-free code and still have well-defined programs. So you can tag every load or store with a special atomic tag telling the compiler, I know that this access may be racy. Don't consider it undefined. Instead, give it this or that semantics. So the first such tag is sec_cst, which is the stronger one. So it is the most expensive. It pretty much always requires at least one fence. And so this is the first example that we saw that was failing on x86 once fixed. So sec_cst says that if all of your accesses have this attribute, then you can get the result just by looking at the possible interleavings of the accesses. However, we saw that, for example, on we saw that for this we only need a fence on x86, not on ARM. So it would be wasteful to use the expensive sec_cst attribute, because then the compiler would add fences even on ARM. So you have a cheaper one, actually a pair of a cheaper one called a release acquire. The meaning is that whenever you load with an acquire tag something which was stored with a release tag, everyone after you will see everything that was done before that release. So it creates some synchronization. And so here, for example, the load of ready, because it is acquire, if it loads from the store that is released, then it will also see the new value of x. So one obvious question is what kind of impact does this have on all the compiler optimizations? So one simple example is a loop invariant called motion. So here we have code where in every iteration of the loop we are updating x, and the compiler would like to just do one store to x at the end of the loop. So is this correct? Well, it is tricky because n can be equal to 0, 0, and then you have no iteration of the loop. And you are just saving x to some temporary variable and then restoring it. And this is unsafe because you may have another thread somewhere else modifying x. And x has no atomic attribute. So it... yes, it is just a pointer.
Plus star x, you're modifying.
Oh, yes. Yes. Indeed. Sorry. So yes, we may have another thread which modifies the memory pointed to by x, and so it is undefined. And actually, in this case, it is even unsound because we may overwrite the new value of x, star x. So a simple rule is to never add a store on a path where there could have been no store to that variable, because you are introducing a race, possibly because you cannot know what another thread may be doing at the same time. Now, what about eliminating things? It seems much safer than introducing them. So for example, here, the usual condition on eliminating the store of 42 into x is that you have no access in between the two stores that alias with x. But for example, if you have this code in between with neither flag 1 nor flag 2 aliasing x, it is still unsafe to eliminate x, x equals 42. Because you can have another thread which is reading x and then printing it, and you very much want that other thread to see that x is 42. So it is not safe, at least in this case, to do the dead store elimination. So an interesting point is that if you only have an acquire, then it is safe to eliminate x equals 42, because any possible read of x in another thread would be racing with that store to x. So the compiler can be thinking, well, I assume that the programmer is careful, is not using any undefined behavior. So I know that no other thread is modifying X or reading it. Similarly, if we only have a release and no acquire, we are safe. So the only issue, the only hazard is if you have a release followed by an acquire, because then you can give control to another thread and then wait and take back that control all without any kind of race. So we saw that optimizing non-atomic accesses near atomics is dangerous, and we must be careful. So another idea is, can we optimize the atomics themselves? So for one example, if you just compile every access one by one, you will need an arm to add a fence after every acquire load and a fence before every release store. And this seems wasteful because you may get two fences in a row, which is not stronger than just having one fence. So you have one unused fence. A slightly trickier case is if you have some control flow in between, because here you cannot remove any of the two fences without breaking some ordering with the other store. But you still have two fences in a row on the main pass. And so more optimal placement for the fences would be either this or this, which in both cases guarantees exactly the same orderings, but you only have one fence on the main pass. So I looked at how to do that, and it is fairly similar to the issue of partial redundancy elimination, in that you want to move some fence to another pass to be able to eliminate it on the main pass. So I implemented an algorithm from the partial redundancy elimination literature, which is built on top of a min-cut. So first, you build your control flow graph with one node before and after every access, and one node at every point where the control flow splits, and one node at every point where the control flow joins. Then for each fence, you put every access before it in the source set, and every access after it in the sink set. You do the same for the other fence. Then you put for each edge how much it would cost to execute a fence on that edge. So, for example, here we put int max on the cross edge, on the cross block edges, because we don't want the complication of adding fences there. But we can use the frequency of execution to see that these edges are more costly to have a fence than these. And then you just do a min-cut and put the fences on the min-cut. And so the idea is that you guarantee that you will have at least one fence on every pass, from an access that was before a fence to an access that was after that fence. So it is guaranteeing exactly the ordering conditions that you want, but you are minimizing the dynamic cost of the fences. Yeah, and so we get exactly what we were hoping for. So it may seem a bit too much work for just this, but there are many other patterns that it can be extended for too. For example, a common thing in spin loops is to wait on an acquire load. So you are doing a load acquire again and again, and in every iteration you incur the cost of a fence, which is creating some kind of a contention. So you would like to sync the fence outside of the loop. This is fine to do because the ordering between the different loads is already guaranteed by the processor because there are laws of the same variable. So you can't have any kind of weird issue. You only want to synchronize with whatever will happen after the loop. And so if we look at this from the...
what does LDR0 come out? R0 do?
Oh, this is just loading into R0 the value which is pointed at by the current pointer in R0.
But that's not added bucket.
So
We're tracing a link list.
oh yeah, right. Yes, right. It should have been R1. Yes. So yeah, I should have. I tried to minimize the assembly and I minimized too much. Thank you. Yeah. So if we look at the control flow graph, the issue here is that this axis at the top is also in the sync set because of the loop. But we can just teach the algorithm that whenever it is tracking a fence which was introduced by an acquirer, it should skip that access when building the sync set. And then this will automatically sync the fence because as soon as it can be sunk, it will be much cheaper to do outside of the loop than inside of the loop.
I think that's the wait for the fix stuff. You know what's the impact of that with increasing memory content. You're replacing the partially local wait with something that always accesses your process. I'm not sure what you actually want to do with that.
I am not entirely sure, but I think that the fence can have some global impact because you must communicate with the other cores. So I think if you just want to reduce the content tension, it would just be a matter of adding some no ops or some sleep instead of a fence. No.
That part depends on the implementation.
Okay. But it was just one example of the way that it can be extended in various ways for different patterns. So then I also looked at what LLVM was actually doing on simple example and found that there are lots of small things and patterns to fix. So one example from a paper by Hensberg is that sometimes when you have a sec lock, you would like to end a critical section with a load. And so to have the right ordering and to make sure that nothing can be sunk out of a critical section, you would like that load to be released. But there is no such thing as a release load in C11. So one way of trying to make it will be with a fetch and add of 0, which is a release. Because then you are saying, I am doing a store, but that does nothing, which is release, so that indeed acts as a one-way fence and keeps everything before it. And I am also getting as a side effect the value of x. But if you do that on x86, for example, you will get an instruction. So here, an exchange and add that will touch the cache line in writing. That will try to write to it, even if it is exactly the same value. And so it will add some content tension because you will ask for an exclusive access to that cache line. And so one cheaper thing you could have for this would be to see that, well, I am never modifying x, so I may as well just load it. And in practice, sadly, you still need a fence for this because of the taste of release, but it is still useful because you are reducing a lot of contention, and so you are improving scaling a lot. another example is in the choice of which fences should you use. Because most architectures have some heavyweight, expensive fences like heavyweight zinc on power or DMB SY on ARM. And for release and acquire, you can do cheaper things like lightweight zinc and DMB-ish, which were not always done. But even better, you can do optimization for specific processors, because, for example, the Apple people told that for their Swift processors specifically, DMB HST is strong enough for release. And so this is, I think, a good reason to use atomics instead of rolling your own with assembly. It is that you cannot hope to know every special tricks for every possible processor, but the processor writers, makers, can teach these tricks to the compiler. And so, for example, LLVM does this. If you tell it, I am running on that specific machine. So another simple example was a bug with stores of immediates, which was using extra registers. A more funny one was on power, where you had this horrible code when you were just storing a byte to a byte. So first you had all kind of shuffling of the bits, then a loop, doing a load link on a store conditional on every iteration of the loop. So actually what was going on here, which is quite funny, is that the backend, instead of just saying, I have a store, so I should make a store, was saying, oh, it is an atomic store. I don't know what I should do with that. So the middle end was helpfully replacing every store by a loop of compare and exchange. And then every compare and exchange was replaced by some load linked and store conditional that take a lock on the cache line, basically. And then because these are only implemented for words in the power backend that are well aligned, you have all of this shuffling, which is trying to align things in the right way. And so actually all this can be replaced by just I put 42 into the register R2 and then I store a byte. So that was a pretty big win. However, not all is perfect with atomics, even if now you can get some decent performance, because there are some other attributes such as relaxed. So the idea behind relaxed was sometimes the programmer really knows best, so they should be able to say to the compiler, I know I have a race, I want it to be well defined, but don't add fancies. I know what I am doing. So, for example, this means that you can print 1-1 in this code, because why not? The processor could reorder the store on the loads. Why not? But because C11 standard is defined in terms of traces of events, from its point of view, this looks a lot like this, where instead of a constant, you have some dependency and basically some kind of loop where you are storing some value because you loaded that value because you stored that value. So after this, x equal y equal whatever value you want, which is pretty scary. But you can make things even worse, because you can have causal loops where you will enter in a branch because you entered that branch. And so you, from this thing, you can build all kinds of crazy counter examples to pretty much any kind of analysis or reasoning you may wish to use. So it is a pretty big question how exactly this should be fixed. And the main thing that most fixes would add some small cost to relaxed, so they would not be perfectly free as they are currently in trying to restrict this kind of craziness. Another attribute is a consume. So consume is kind of a cheaper acquire. So acquire was for a load to make sure that everything that comes after it will see everything that was before synchronizing release. Consume says that everything that comes after it and that depends on the values that was loaded will see everything that came before the synchronizing release. So for example, it will work here exactly like an acquire because we are reusing the same key. If it was another variable without any kind of difference, it would be exactly like a relaxed. It would not order anything. So this was a good idea at first glance because it is really cheap on hardware. Because ARM and Power, for example, require fans for acquire, but not for this, because they automatically track such dependencies. However, the big issue is that dependencies are not defined as cleanly at the C level as on the hardware level. For example, here, do you have a dependency or not? And the answer is that you do until you run a compiler that optimizes t minus t into 0. And this can be really messy because instead of just a single inline expression, you may have a call to some function somewhere else, meaning that to keep the dependency here, you would need to prevent optimization everywhere, which is obviously not a good idea. So what compilers currently do is they say, whenever we see an acquire, we put a fence, exactly like acquire. But this means that in many patterns, you will need a fence where the inline assembly approach would not. And this is why, for example, the Linux kernel is not yet using atomics, because this kind of thing is a very common pattern for them, and they don't want a fence, and they don't want either the compiler to optimize their dependencies away.
How does consume interact with function calls? How does consume interact with function calls?
How does a consume interact with the function calls? So in theory, you are supposed to track the dependencies throughout the function. And in a practice in the Linux kernel, where they are using their own handmade consume with assembly, this is exactly what they do, and they sometimes have long strings of functions, and they are carefully making sure that the result at the end really depends on what was at the beginning. And so the main suggestion for how to fix this is add a way for the programmer to annotate and say, in this function, I want you to preserve my dependencies, or even finer grained. I want you to make sure that this variable depends on that one at this point. And so there are lots of ideas on how to do that, but nothing that really made a consensus yet.
There actually is spec along those lines in the C++ standard, but nobody else knows. There's a trace dependency.
Yes, so...
Trace dependency you don't know of. The compiler is allowed to ignore it. It doesn't actually change the semantics.
It doesn't change the semantics, but it's a hint that it might be worth preserving dependencies rather than it's something very defensive.
Yeah, so the comment was that there is already a carries a dependency in C11, which aims to do exactly that, but it has various limitations, and you can't really say exactly what you want, and so compilers can't really use it as much as they would like. So in short, I hope that I convince you that atomics are much more portable than inline assembly for this kind of log-free code, and that they can be well optimized by compilers, even if it is somewhat tricky, but that there are still lots of open questions to answer on the exact details of some parts of them. Thank you.
All right, thanks, Robin. So if there are questions, either come in front or we'll repeat the questions. There's a microphone here. Yep.
So errata for processors, there can be a lot of errata for synchronization. So like Cortex A9, DMB's SY is like the only thing you can do effectively. Do those defeat the compiler optimizations that you've done? Like, do you have to generate to a worst case?
So the question was about tricky processors which only implement some kinds of expensive barriers. And so currently, yes, we only apply the optimization for some specific fancies. And so if we must choose some more expensive one, we are basically saying, okay, I don't do anything, I am conservative. But it is not an essential issue, it is just that no one really bothered to optimize that case.
All right, well, that's it. Thanks for coming.